Initiate the boot sequence platform engineers. Today, we're compiling the ultimate explainer on the May 2026 open source AI inflection point. We're ripping open the raw system blueprints to see exactly how foundation models, weights, and context windows have evolved. So if you love deep dive architecture flows, you are absolutely in the right place. Looking directly at the telemetry from late May, the core takeaway is this violent, industry-wide shift away from brute force, dense parameter scaling. I mean, the days of just throwing massive arrays of VRAM at a monolith, they're officially behind us. We are moving toward extreme hardware efficiency. Okay, let's run through the system initialization check. We'll be hitting foundation weights, bare metal kernels, speculative decoding, agent orchestration, and finally, deployment economics. Layer 1, foundation weights, and the sparse architecture shift. So check out the architectural juxtaposition here. We're abandoning those massive, power-hungry, dense monoliths for highly sparse mixture of experts, or MoE topologies. This cybernetic shift is exactly what allows us to maximize theoretical reasoning while aggressively slashing our active VRAM footprints. To really grasp the sheer scale of this efficiency, just look at DeepSeek V4 Pro. It boasts a massive 1.6 trillion total parameters. But here's the kicker. Its hybrid attention mechanism violently constrains memory computation, activating only 49 billion parameters per token during a forward pass. You're getting trillion parameter reasoning on a fraction of the compute budget. And we're seeing this sparsification mirrored across the entire ecosystem. Take Alibaba's Qwen 3.6, right? 35 billion total parameters, but it only activates 3 billion. Compare that to Meta's Llama 4 Scout, which routes its 17 billion active parameters across 16 experts. These highly optimized topologies are what enable frontier-class agentic programming natively on constrained consumer workstations. It's a real game changer. Then you have Google's Gemma 4, nailing this edge-to-server continuum perfectly. It scales from 2.3 billion parameter-dense networks built for low-power IoT hardware straight up to a 26 billion parameter MoE. And that MoE topology is so ruthlessly optimized, it effortlessly crunches 80 tokens per second, even if you bottleneck it with legacy DDR3 RAM. Literally insane. Moving down the stack to Layer 2, bare metal kernels and hardware-aware execution optimizations. Look, if you're trying to squeeze 35 billion parameters onto an 8GB laptop, you need to execute exactly like this terminal prompt. In llama.cpp, using these specific flags pins your most active expert layers directly to VRAM. It disables memory-mapped file loading, and that mlock physically locks your model pages so you prevent your OS from catastrophic swap thrashing. But managing weights is only half the battle. As context windows hit the 1 million token mark, the KV cache footprint just absolutely destroys your VRAM, which is exactly why the kernel community merged the TurboQuant extreme compression algorithm. It's a C++ data type that compresses context caches 3.5 times more efficiently than standard FP16. The underlying mathematics here are just brilliant. The algorithm executes a randomized Hadamard transform, applies fast Walsh-Hadamard preconditioning, and then hits it with a 3-bit Lloyd-Max optimal scalar quantization. Bottom line, we achieve 3-bit KV caching without catastrophic precision loss, literally saving our local rigs from the Linux out-of-memory killers. And for the Apple Silicon users out there, the Swift LLM stack is a total paradigm shift. It's a zero-Python metal-native inference server. It uses direct memory access to preemptively stream MoE weights right off your NVMe SSD. By completely bypassing standard CPU routing, it makes M-series chips deadly competitive with dedicated NVIDIA CUDA arrays. All right, Layer 3, speculative decoding and decoupled torch spec paradigms. Notice the friction in legacy setups here. In traditional autoregressive systems, your drafting and target model verification share the exact same GPU compute resources, and that creates massive hidden memory bandwidth bottlenecks. But by integrating the Eagle 3.1 algorithm via TorchSpec, VLM physically decouples the training and inference pipelines. So, here is exactly how we fix that bottleneck. The target model pushes out maximum hidden state throughput, and then TorchSpec uses the Mooncake engine to stream those states to a completely separate parallel training cluster. It completely decouples the inference engine from the draft training workers on the fly. It's beautifully efficient. Ascending back up the stack to Layer 4, agent orchestration and stateful multi-node frameworks. We have officially moved past basic, stateless chat loops, folks. We are now deploying highly durable graph topologies dominated by the Microsoft Agent Framework, LangGraph version 1.1.10, and Mastra. These frameworks embed native programmatic support for complex sequential execution, concurrent branching, and even time travel debugging. And what's absolutely critical for the enterprise web devs compiling the stack is Mastra's v1.0 pivot. Transitioning to the highly permissive Apache 2.0 license unblocks unrestricted commercial integration, meaning you can now bake native TypeScript agents directly into your React and Node backends with zero commercial encumbrance. Huge win. Finally, Layer 5, deployment economics, benchmark takedowns, and scalability. When you observe the raw spot pricing per million tokens, the economic advantage is just undeniable. Running a distilled sub-35 billion parameter MoE like Qwen 32B on an optimized B200 instance drops costs to roughly 20 cents. Compare that to a massive dense deployment on an 8-GPU H100 array costing nearly $6. The efficiency of agentic routing on local architectures is an absolute financial landslide. And the data is our ammo here. On SWE Bench Verified, Zeta AI's open-source GLM 4.7 Flash is now ripping a 59.2%. It completely outclasses previous dense competitors and establishes absolute local supremacy for UI generation and complex tool calling workloads right on your workstation. Take a look at the current state of the May 2026 LLM leaderboard. While closed APIs like Claude Opus 4.8 and Gemini 3 Pro still hold the absolute ceilings on humanity's last exam, the heavily optimized local open-source architectures we've just analyzed are fundamentally redefining the Pareto frontier of performance to compute. System compilation complete. Based on the telemetry and architecture flows we've just covered, here is the final variable to evaluate. Considering what you can now execute locally on bare metal, is your expensive closed-source API dependency functionally obsolete for standard enterprise workloads? Think about that as you update your own stacks.